are we doing?
Hi, Dr. Tripp.
Hey, Olivia. Or Melissa. It was Olivia's chat, so hi, everybody. Okay, what are we doing? I saw you started the meeting, Melissa, so you go first.
Okay, I'll share my screen.
Oh, don't do this to me. No, you guys are fine. It's just my tablet's decided that it doesn't want to recognize the internet on campus.
Okay.
Okay.
My first question is regarding when having two bonds to decipher between and where the radical goes. So, Can you see my screen?
Yeah.
Okay, so here, when I was doing this is basically formed as a radical, and then we have three options of where that radical can go, but I'm not sure where it goes because here there's resonance as well as here. So I know this option's basically out, but I'm not sure how to decipher between these two options.
Okay. So I think it depends on making bonds. So in the middle one there, you're making an oxygen carbon bond. And that's much weaker than a carbon-carbon bond.
Oh, here.
Yeah, that's much stronger.
Okay.
So I'm going to say I haven't drawn any examples where the radical attacks a carbonyl to make a carbon-oxygen bond. And I've actually never thought about that until you just shown it to me right now. And I'm thinking through, okay, why doesn't it do that? And I think the answer I've got for you is the oxygen carbon bond is a much weaker bond than a carbon-carbon bond. So it's not going to form that preferably, even though I think you are logically saying, hey, a carbonyl and a carbon-carbon double bond, I'm not sure which of those is stronger. It seems to be case by case, which you're absolutely right. But I think it's the carbon-carbon bond forms, so you get that.
Okay. Okay. And then I was wondering, when we have something that is reacting by, okay, first of all, this should not be a nitrogen, that should be a sodium. When we have something reacting by E2 and we need that anti-periplanar, so if we had something like this, where the H is, it seems to be not anti-periplanar, but are we allowed to just rotate this like this and then it can attack it?
Would there be any reason you would not be allowed to rotate that?
No.
Right.
Okay.
So will those lead to different products, though? If you didn't think about the anti-periplanar, this is a good question. If you didn't think about the anti-periplanar thing because you're not as good a student as you are, then if you eliminated from the top the first rotamer, or you eliminated from the second one that you drawn in gold, would you get different products?
If I actually did do this instead of
if you did the one in black instead of the one in gold. So gold is correct, where you have the anti-periplanar. We haven't discussed it. It is possible to do syn-periplanar when the hydrogen and the leaving group are on the same side. It's much more unlikely. It only occurs in very rare circumstances, so we're not talking about it, but it is theoretically possible. Would your gray and your gold ones give the same product?
I would think not.
Right. How would they be different?
So this one would be not cis.
Yep.
Z. So Z. And then this one would be E.
Right, exactly. Absolutely perfect.
Okay.
Perfect,
would it
perfect.
be a major and minor thing, or would it just be one product?
No, you would just get the anti-periplanar.
Okay.
It's just, there are some really weird examples where you do get syn-periplanar, but we're not discussing them because it's complicated enough.
Okay.
And there's case by case things, and it's really odd things, so it's fine.
Okay.
I haven't lied to you at all, so it's all good. Okay, yeah, that's good.
I think this was basically the same question, like which one do we draw? Because we don't. Sorry, I'm just looking and orienting myself. Oh yeah, this is a case where we don't have a stereo center, so you can draw both. Yeah.
Well, what you're gonna do is you don't. Let me carefully think about this. You don't have a stereo center, but that doesn't mean that those protons. Okay, there's a. What you might want to do is you might want to look at what's the most stable Newman projection.
Okay.
Because the most stable Newman projection will lead to the form that this thing sits in, and one of those hydrogens will be anti to the bromine and the other won't. And so, although the hydrogen that is not a stereocenter, because it's adjacent to a stereocenter, the hydrogens kind of act a little weird, because if you remove one, you can get E. If you remove the other, you get Z.
Yeah, that's
as you've
what
drawn. And those are two different products.
Yeah.
So is there a preference for E or Z? And the answer is yes, and it depends on which is the most stable Newman projection of the starting material.
Oh, see, I did it the way we did it in class, where like E is more stable and then Z is less stable.
Generally, yeah, that's true, but it is going to be from, because you need, once you make the double bond, if it's an E2, E2s are kinetically controlled. Like you make the product, it doesn't go back. It's not reversible. And so if one of the Newman projections is more stable than the other Newman projection, it'll lead to a lower energy transition state, and it will lead to the product. So the products might differ a little bit, but in this case, because you have one of them is going to be more stable than the other.
Okay, I know we did an example in class where we like drew both but indicated major and minor. So do you want us drawing both when there's like two hydrogens possible?
Yes, if you're right. Like if you got the major and minor right, I'd have to draw the Newman projection. I can't do this by inspection. I have to actually draw it.
Okay, and then
I don't know which one of those is major off the top of my head.
Oh, okay, yeah. I just wanted to know that like we'd be required to draw both.
I think if I said consider stereo, yeah, you know what? Yes. Well, I think if I said consider stereochemistry, I think you'd be required to draw both. But in some of the cases, I'm not caring so much about that. My question is more about which of these protons is going to be removed.
Which still requires you to draw the Newman.
Yeah.
Okay. Okay. And then from the Newman, you just okay. Yeah, I know that. And then this question. So when do we? What I was confused with was like I don't want to go into the exam like losing marks over like knowing when to draw stereochemistry versus not when to draw stereochemistry. Like things like hydroboration, like epoxide formation, like adding the hydrogens. Like I know all of those basically like you add the hydrogens, for instance, like they'll be on the same side, but do we have to show that with dashed and like wedged lines when we're doing these
I would say it's safer. Yes.
Okay, would we lose marks for like not drawing both possible products?
No. Unless I say draw both possible products, you will not lose marks for not drawing both possible products.
Okay.
I might state for questions, if this gives you a racemate, draw both possible products.
Okay.
But if I don't say that, you can draw either one, and that will be okay. I think it doubles your drawing for no particular purpose.
Okay.
Yeah.
Okay. And then this here, is this a primary leaving group right here?
No, it's secondary because that carbon is attached to two carbons.
Okay, so we would still have
Be a secondary leaving group.
Okay.
Like you do have a bromine, like two bromines. And that does add some bulk, but like a bromine is a lot smaller than a CH3. Like whenever you have a carbon, carbons are never alone. Carbons bring baggage with them. Whereas single atoms never do, so they don't affect the steric bulk around the center very much.
Okay. Okay. I'm just gonna check. Okay, I have just a couple questions. For this, is this the only thing that occurs with this molecule?
Your starting material is wrong.
Oh, this?
Yeah. So you reacted something with so benzene rings, those three triple bonds all in conjugation of each other, don't react as far as we're concerned in this course. We haven't seen them do anything, and they're not going to start. They're going to do lots of stuff in the next class, but this course they don't react. So you used one of those double bonds. That's incorrect.
Okay. Where would this go?
So what do free radical halogenations like?
Oh, hydrogen.
Right. So what's the weakest hydrogen bond? Is there any resonance in a molecule?
Only here.
Okay. So is there any position with a hydrogen on it that could participate, that a radical generated that site could participate in resonance?
Here.
Yeah.
Okay. Okay. And then once, okay, I'm just gonna draw. Oops. Okay, and then once, how would this then? What would?
Well,
this
now
be?
draw the bromine where you would have the bromine. Okay. So you wouldn't have the two bromines there. You'd have that as a double bond still. And then you'd have a new bromine where you have a green dot. Okay, now reconsider your question.
Well, if we have, what I was thinking is that, I'm just going to erase this. What I was thinking that was this hydrogen would just react with the hydrogen here.
You're absolutely right. But you have a bromine on your molecule. You dropped your bromine.
Oh, like in the product? So
yeah.
Even though acid-base reactions are the fastest? Like,
right, no, the bromine's still there. You had a bromine in your starting material, you treat that with base, you still have a bromine. But you've disappeared your bromine. You now have a CH2.
So does this attack here?
Not that. I'm looking at your product after. So I'm looking at your product.
Oh yeah, this.
And I'm saying, hey, you're missing a bromine.
Oh, okay.
Okay, now consider that molecule cannot react.
Yes, but I'm trying to think how it would react. So if it's hydrogen's a strong base, so it would probably be an elimination.
Well, no, it's already reacted. You have an O- now.
Oh, so that's it?
H- did its acid-base reaction. No, you're not done.
Oh.
Can the ONA react with something in that molecule?
Oh, this. So then we can go 1, 2, 3, 4, 5, 6.
Perfect.
Oh, okay. Okay. That was tricky.
Isn't that evil? Yeah, that's fine. Those were the bonus questions on that one.
Okay. All right. I think that's it.
Okay, I'm going to let somebody else ask some questions. I know they're all good.
Can I ask a question about? Can I ask a question about the last thing Melissa drew? So when we drew like the mega ring, right? Do we have to indicate stereochemistry for like the methyl and the ethyl groups, or because we didn't indicate it initially? There's no way we would know. I don't know.
If there was no, Melissa, can you just share your screen again?
Yeah.
I don't think so, Dea, because I don't think I actually indicated stereochemistry. So I think you dodged that bullet.
Okay, here.
Yeah, no. See, there's no stereochemistry indicated, so you don't need to indicate stereochemistry.
All right. If you did, we would have to though.
Yes, and then you have to work out how to unfold it. But it was almost like that was more question than I wanted to ask with that. This was tricky enough.
Yeah.
I was like, oh yeah, you got the entire concept right, but then you didn't rotate the bond right, and so your bond is in when it should be out, and it's like that's not what this is testing. You should feel like a great feeling of success when you see that and not be nickel and dime to question. Anyways, yeah, we over. So yes, but if I had indicated, you would have to.
Okay. Trying to join in my iPad here. Forgetting how to do that every week. If you want to let someone else go until I figure
Okay,
out.
let's go to Megan now.
Okay, so for the first question I sent, how do you know this was an E2 and not an E1?
Did you send it in the chat or in the?
Yeah, in the chat.
Here we go. Okay, so how did I know it was an E2 and not an E1?
Yeah.
Triethylamine is a pretty decent base. So it's these amine base. So we've seen E1s when you're under neutral or acidic conditions, and amines are always basic. And I don't think I've emphasized that enough. I think I did talk about in the posted lectures. I have not talked about in the class I've done this year, and there were examples in the text where we've used these as E2 bases, like in the assignments. So triethylamine is always going to work these are always E2 bases. They're basic. It's not like using water or something which isn't basic.
And for the second question, I was wondering why it's not, because the correct answer was, I think it was A. And I was wondering why, like I thought it should give the Zaitsev product, but.
Is the Zaitsev product any of the possibilities?
I thought it would be B.
Is that a Zaitsev product? What is a Zaitsev product? It's an elimination, right?
Right.
Are there any eliminations here?
Well, the question says, what is the major product of the following E2 reaction?
Well, it says, what is the correct product?
For the second picture?
I see sodium cyanide. Oh, sorry, the third picture. Sorry, it's the third one. Okay, I'm sorry. I was looking at the substitutions going, what do you mean? Okay, okay,
no,
you thought, no, no, this one's clever. Okay, so this is coming back to Melitsa's point. Yes, this is a Zaitsev base. You're absolutely right. Is a Zaitsev elimination possible? Is the proton at the Zaitsev position antiperiplanar to the bromide?
Oh, okay, yeah.
It's not possible, so you're forced to do the other one because the other one is impossible. You're absolutely right to be looking at that going Zaitsev base, but one of the conditions of the E2 is it needs to be antiperiplanar, and it's not. As I said during class, I will ask a question on the final exam, which will rely on that, basically be based on that concept. I promise. It's the only question I promised.
Okay.
So now I have your substitution one. Sorry, I guess they're just in a different order when I screened them here. What was your question about this one?
For the third one, I was wondering, for SN2s, is the product only the inverted, the inversion?
Yeah. They're stereospecific reactions. There is no other option. Mechanistically, it must invert.
So for the third question, I thought it was doing an SN2.
And it is.
Then how come the correct answer would be C?
It said C was the correct answer?
Yeah, like I thought it was.
Then it's wrong, and I'm going to go update that right now on Blackboard. Okay. That's wrong. That's wrong. It's an SN2. It is direct inversion. Absolutely. You are completely correct. I changed the question at the last minute, and I thought I had actually also told somebody to change the answer. But you're absolutely right. I am changing that right now, actually.
Okay.
No, you're absolutely right. Do you remember what question number this was? No,
it was the very last one, so 10.
Okay.
I also had a general question about epoxides.
Yeah.
There were some questions where like the three-membered triangle was formed, but it wasn't necessarily like an epoxide reaction. Like sometimes it was, I don't know if I have an example with me right now, but like it didn't use like the MCPBA reagent or anything like that, but it still formed the three-membered ring. I was just wondering, when do we know when to do that?
I'm not sure which example you're talking about. And there's two ways to make epoxides. One is with MCPBA, and the second one is with adding OHBr across the double bond and then treating it with the base, and then you deprotonate the OH and it kicks out the Br and makes the epoxide. So there's two ways to make an epoxide. So if there's, I don't know which question you're talking about, so I can't address your question. Edit your question. Sorry, I'm going in and editing this right now because if this is.
And for
oh fuck yeah, you're absolutely right. Yeah, I'm changing this right now. You're gonna get your grade. I'm really sorry. I have no idea why it's wrong.
Well, that's okay. Thank you.
No, I'm stupid. Sorry. I thought I caught absolutely everything. Okay, go on.
You know that really good leaving group? I forget the name of it, but
OTF or yeah. Okay, yeah.
Is it? I saw like two versions where one of them had CH3 and CF3. Is there no difference? Like they're
the CF3 is much better leaving group, but they're both possible. So there's sort of different versions of it. There's sort of actually, I think there's like 120 variations on it. There's no real need for that. There's like 3 major ones. The CF3 is by far the best because induction, but everything else is there just to kind of tune it to make it sort of the exact right level of leaving groupedness.
Okay, and I have one last question from assignment 3.
Yeah.
Question.
By the way, your mark will be updated. I just changed the grading, so that'll update it immediately. I'm sorry for that.
Okay. Question J.
Assignment 3, question
J.
What's up? Teaching. Question 1J.
Yes.
Yeah. Okay.
I was just wondering. I think this was like a trick question where we didn't use an alpha hydrogen.
Right. It uses a gamma hydrogen. So the idea is that there is no alpha hydrogen to be removed, or there is, but it would make a weird ketene thing. And so instead what happens is it kind of takes away a hydrogen in conjugation with the other double bond. So let's call it an E2 prime reaction. It's an E2, but we have an extra double bond that kind of helps out. It just kind of extends it out 2 carbons.
When do we know when to do this?
I promise not to ask you that on the exam, but then the other thing too is that it actually is generally faster. These reactions, there was a question in a textbook which a lot of people were having trouble with, and it was an SN2 prime where SN2 did the same thing. It attacked the double bond instead of the leaving group, and the double bond kind of shuffled over and kicked out the leaving group. And it almost always happens that way if it can, actually. So if there is a double bond in conjugation with the leaving group, the reaction normally proceeds by the double bond kicking out the leaving group, and either your nucleophile or base working 1 carbon over. It always goes that way. And I think it's because it minimizes hindrance. So even SN2s, like the E2 is clearly impossible here, but an SN2 would be possible, but it still doesn't occur at that site of the leaving group. It occurs a carbon over. It's kind of like the SN2s kind of become an SN1. Like if this was an SN1 or an E1, you wouldn't blink at considering the resonance structure and where you want to do the deprotonation. But because it's an SN2 or an E2, you don't think about that. But that's molecular orbitals are molecular orbitals. They're spread over the entire molecule, and I'm realizing I'm not making a lot of sense. But we haven't discussed this in a lot of detail, so I'm not going to go after you about this in class or on the exam. Always is my answer. It always does this if it can.
All right, thank you for your help.
Okay. Dea, did you find what you were looking for?
Yeah. Okay. Let me share my screen. 'Cause I have a couple of questions. Okay. So not sharing yet.
No, it's not sure. I don't see it. You have to share content and then you have to hit the specific screen you want to share. So it's kind of like a 2-click thing on Word or Teams.
I don't know why it's not show, because I'm showing it through my iPad and I did it before. Broadcast. Start broadcast.
Yeah, is it loading Dea and then like the Microsoft
Yeah,
thing?
no, it says it's broadcasting, although it's not showing anything on my laptop.
You shouldn't be broadcast. You should be sharing.
Yeah, it on the iPad calls it screen broadcast.
On Teams?
Yeah, because I'm on my iPad and my laptop.
Okay.
Maybe I should. Okay, hold on. Let someone else ask again. I'll
Mess
just run
around with
straight
it,
from
and
it.
if your screen sharing suddenly pops into our thing, I'll forgive you.
Okay.
Okay. Olivia.
Good morning, Dr. Trant. How are you?
I'm good. How are you?
I am doing okay. So I just had a few questions for you from the assignment.
Yeah.
So I just put them in the chat.
Okay.
So for the first one, about which reaction would be faster.
Yeah.
So obviously, like the A structure has a tertiary carbon, which is better. But I was wondering for B, if we did a hydride shift, then would that make that one better because then I is a better leaving group, or am I thinking about that wrong?
Okay, so we have not discussed hydride shifts, but you're fine to think about them. But to get the hydride shift, you would need to make the carbocation first.
Okay.
And the carbocation formation is going to be slow because it's secondary, even though I is a better leaving group.
Okay, no problem.
Yeah.
And then that makes sense. And then for the one underneath of it, I was just wondering why the ring wouldn't form, because we had done a question very similar in class, except it was with iodine and then a different base. But I just didn't know why the ring wasn't forming in this question.
You're not the 5-6. You're a little bit too big, and so it's going to slow down compared to if there's nothing else in here, so there's no solvent or anything, there's just a lot of this starting material, which is a liquid.
Mm-hmm.
Then, like if this was run, so I think that this is kind of a borderline case, but if there's just a lot of the starting material in there with no solvent, which is what's indicated here, then it's going to find another molecule itself before it can cyclize onto itself.
Okay, so really we needed like a solvent in there.
You need a 5 or 6. Yeah, if you had a lot of solvent and said dilute, then it would have 7 would have a chance of forming. 8, even if you're pretty dilute, it's still going to go intermolecular instead of intramolecular.
Okay,
But 5 and 6 are the ones that we're sort of going, hey, those are the ones where ring formation predominates.
Okay,
Ring
that
formation is
makes sense.
not impossible, it's just not going to predominate.
Okay.
Yeah.
Thank you.
So Rawan asked, this might be a really dumb question. What exactly do you look for when a ring will form? 5 and 6. Daya, I can see your screen. I just see the Zoom window. Now I don't see it. So that worked, whatever you did, but we just saw ourselves. Do you want to try again? If not, I'm going to jump in on Chloe. Oh, there, you're sharing your screen. There we go. Sweet. Okay, I'm seeing your MS.
Can you hear? Can you hear me now?
Seeing your questions window.
Can you hear me?
Yeah, I can hear you.
Okay, that's great. So I just had a couple of questions, I guess, about general stuff. There's some, like, the most general question I have is, you said it's cumulative, but how cumulative is cumulative? Like, are you going to be asking us to draw the double Newman of something?
I could, yeah. Well, I think what I might do is I might tie that into the other questions. Like, it is fully cumulative.
Oh, I get.
I can ask you anything at any point about anything.
So like close the ring and then draw the double Newman.
Yeah, or I could say, you know, explain the explain why this elimination goes using a Newman projection. Yeah, exactly.
Oh, so like
it's fully cumulative. Yeah. I'm sorry, like the first stuff we just build on it. We just build and build and build and build and build.
Yeah.
None of it's gone away.
It's not gonna be like direct questions, just like straight up, what's the Newman? More like do this and then draw the Newman.
Yeah, more likely, yes.
For those questions, like if you for some reason messed up the first part, you'll still get full marks for the Newman if you draw the right Newman based off what you drew.
If you project, yeah, if you make a mistake, you make a mistake, and if you then carry your mistake through, you'll get the marks. Yes.
Okay, so you just lose marks for the initial mistake, not having a wrong Newman. Also.
You don't. Yeah, you don't lose the marks multiple times, which is why it's a choice.
Okay. Other question. In your recorded lectures, you go through something where you put like KMNO4, NaOH, and H2O in heat, and you get something like ozonolysis.
Yeah.
Is there a difference between the two? Like, okay,
nope.
Mechanistically there is, but like product-wise.
No, except the ozonolysis is a lot more is cold and much more selective. So there's all sorts of things that heating with KMNO4 and sodium hydroxide are going to destroy. Like if you have any other leaving groups on your molecule, any bromines or any kind of halogens, say goodbye to those. Whereas the ozonolysis will just surgically destroy your double bonds. So they're both completely, they'll both do this. KMNO4, strong heat, and lots of base can destroy other stuff too.
So, like in an actual lab setting, you'd probably just go with ozonolysis.
Yeah, if the molecule is remotely complicated, we use ozonolysis all the time. Like when we do this in my lab, we use ozonolysis. We've got a special ozonolysis machine to do this.
Okay. So of the four mechanisms that I consider kind of batshit crazy, which ones do we actually need to know, and which ones do we need to like memorize essentially?
Well, this is an open book exam.
It's like you're gonna ask it, like, okay, I guess. At some point, it's just regurgitation of information. Like ozonolysis, I don't think.
I think I said I will not ask you for the mechanism of ozonolysis. All the rest are fair game.
Fair game, okay. So everything.
And I agree with you. Those are kind of the batshit crazy mechanisms. I think oxygen recreation is not as bad, but the other ones are bad. I agree.
Yeah. Okay.
But you're responsible for the results of it.
Yeah.
Yeah.
For sure. I don't know what I was asking with this one. I'll try to figure it out.
I don't know what you're asking either.
Yeah. Okay, so for this one about the alkene assignment that's just epoxy formation. I guess about epoxies. So I guess my question is about epoxies, like how do we know which side the ring forms? Because
which side of that's more hindered?
Okay, for this one it's obvious you want to form it. Okay.
Right. So if it's obvious, that's how you know which side it forms. And if the molecule doesn't have stereochemistry, doesn't matter. I might have drawn only one answer, but the other one would be perfectly fine.
So if you get something like this, and then you have something like that,
yeah,
would both in and out be valid structures?
Yeah.
So for something like, I guess the real question is, this is from one of your lectures, for I think oxymercuration, you chose to draw the mercury out of the page, and then you fold up with the thing, and then you got this. How you draw it into the page would have gotten like the enantiomer. So would both have been valid? Okay, so both would have been valid answers.
That's actually not, and that's actually not chiral, right? Because it's got two methyl groups, so it's an achiral molecule. but yes, both would have been valid. I like drawing out wedges. So I default to drawing out wedges. It is completely arbitrary.
So unless it's like visibly sterically hindered from somewhere else, both would be valid technically.
Yes. And as I think Melitza asked us at the beginning, unless I'm specifically saying draw both enantiomers if it's a racemate, you only need to draw one.
Okay, that makes sense. I want to know what answer base. I think I was just
Thunder
opening. Yeah. So, and I guess the thing is, if you have like epoxy opening under acidic conditions, and you have both in and out as possible, wouldn't you technically just get all possibilities?
Well, if you have an epoxide open under acidic conditions and you can draw both outer open and you're just opening with water, you're going to get two molecules. They're going to be trans. You're going to get the trans hydroxyls.
Yeah.
There's two ways to do it. And yeah, and it's a 50-50 mix. Yeah.
Okay. Yeah. So for this one, I'm pretty sure I'm right. Is this one just two SN1 reactions?
No.
Oh, yeah. See, I was looking at so the first one.
So when you have a double bond, which bromine is the first? So is this an E1 or an SN? Like, is this a unimolecular or bimolecular? So we're looking E1 SN1 or E2 SN2?
I'm pretty sure unimolecular would not.
I agree completely.
Over here, sterically hindered. Oh, you're looking probably E1 SN1. E2 is possible, but then you have a weak. It's not
weak base. You're neutral acidic. There's no real push. So, okay. So next question is, which of those leaving groups is the better leaving group? And I like they're both bromines. I get that, but which one's going to give you the more stable carbocation?
This one over here.
Right, because it's resonance stabilized, and it's resonance stabilized with a tertiary carbocation. Now it's resonance stabilized, so it's a double bond. It's got a double bond. The most likely thing to happen when you have a double bond is eliminations, because then you'll get two double bonds in conjugation with each other.
Okay.
So it's going to be two sequential E1s.
Oh, you'll eliminate this first, and then you eliminate this second. Okay.
Yeah, and they'll be both in double bonds. Yeah.
So I was looking at it, and SN1. That's what I want to ask. Two SN1s didn't make sense to me. Like that kind of seems stupid, but then that makes more sense when you do two eliminations back to back. Yeah. All right. Oh, I guess also what I was gonna ask, with like SN1, say you have like the molecule is like this. I guess like this, and then but you somehow get a resonance structure to do this. I can't come up with an example off the top of my head.
Well, if you don't have any double bonds, you can't do a resonance like that. But like, let's say you had a resonance structure where you had a double bond in conjugation with a secondary carbocation in conjugation with a tertiary carbocation, it would react from the tertiary carbocation.
Yeah, so like
because we have
off, yeah, I guess the question is, would it kick off the leaving group, then technically do its resonance to get the more stable carbocation, then do the SN1 where the thing comes
right, because the nucleophile is going to react with the site of the greatest amount of positive charge, and the greatest amount of positive charge is going to be at the tertiary site because it's more stable there. So
yeah.
Yes.
What else?
Can I ask a question about that one?
Yeah.
So when I did this question, I did two SN1s because the ethanol was like stick-like. So if we say why we do an SN1, would we get the marks, or is this strictly elimination?
You would probably get like 80% of the marks.
Okay. So
if you sort of said I considered both, because having two double bonds in conjugation with each other, unless something is a really, really crappy base, it's going to do that. E1 starts to dominate the over SN1s at that point. They just do. Okay. And we've discussed that. So I feel that's fair. But you would not lose all the marks or anything. It wouldn't be like 0 or anything. You'd probably get a 3 out of 4 if you justify it.
Okay.
Yeah, because I was like Melissa, and I said, okay, stick like weak. That probably just do SN1.
But you'd also, I want you to show that you've considered the elimination if you're giving me that answer.
Oh yeah,
right.
It's like would you draw like maybe like a T table? So like why we considered E1, why we considered SN1.
Yeah.
And we said this one's better because 1, 2, 3.
Yeah.
Okay. This one I think was the same question we asked at the beginning. If in E2 you have 2 hydrogens available, do we decide through Newman or through the opposite sides?
You decide through Newman.
Always. So the most stable Newman of the initial of like the.
Yeah.
Yeah.
It will almost always. What's funny is the most stable Newman will often lead to the E.
Yeah, but it's not like hard.
Almost by definition, but it's not always the case. And it gets a little complicated if you have multiple substitutions on both sites. But in general, stable Newman will lead to the E.
Yeah, I drew the Newman for those 2 questions, and at first it took me a while. I was like, how do I draw a Newman for a double bond? But is it just along the double bond? And then they just don't move. They're both like
yeah, they're stuck.
Eclipsing each other. Okay.
Yeah, and that's it. They got no choice.
Okay, I guess for this one, like when we draw a mechanism, do you want to explain every step, or do we just arrows are enough?
Arrows are enough. So you would go like, okay, oh well, we made an O minus. The O minus is now attached, kicks back out the ester.
This,
yeah, and then come back down and kick out the ester. Yeah, you'd have to draw out the individual steps.
Okay.
Okay, that sounds good. I think that's all. Oh, there's some more. Oh yeah, I was gonna ask. You already answered this one. I don't think we didn't talk much about any because I got that question wrong yesterday because I didn't realize it was strong base. I just assumed it was kind of. I mean, I should in hindsight.
It's in the textbook. I know it's in the textbook. I know I've asked Simon questions about it. I know I did not cover it this term. Yes.
Yeah, and it's a fair question. I was going to ask about it.
Yeah.
And also, if you have like TSOH, like what would the properties of that as like a
reagent? Oh, it's a strong acid.
Strong acid.
It's like sulfuric acid. So if you draw, I think again, I decided to leave it in because I think I have mentioned it at some points in some of the lectures online. But it's like sulfuric acid, but stronger. Because we talked about the structure of that thing, and it's basically sulfuric acid, except instead of having an OH, you've got a toluene group, and that stabilizes the charge better than having another OH that can also deprotonate. So it's a super strong acid.
Okay.
Just like lose that H, and boom, it's overkill. It's amazing.
So
you see this, you think extremely acidic conditions, and then you just
it's like sulfuric acid.
Okay. So it would be. So it's not a base.
No, it's an acid.
Okay.
Like again, really good leaving groups are the conjugate bases of really strong acids.
Mm-hmm.
Yeah.
By definition, because strong acids are strong acids because their counterions are really stable, and really stable counterions are really good leaving groups. So really good leaving groups are always the conjugate bases of really strong acids.
So would this tend to react
in like the ones, like SN1E1?
Yeah, if there's any tosic acid, it's going to protonate something. It's a source of H+. So
it's probably not like
SN1, probably not SN1 because it's bulky. Probably like E1.
Well, it on its own is normally a catalyst. It's not normally the only thing in there.
Mm-hmm.
Normally it'll be in there with solvent, and a solvent will be your nucleophile or base or anything that you need afterwards. This is just going to give you the H+.
Okay.
Yeah.
I think you asked the question where this was just the only thing in it yesterday on the assignment.
Then I think you could do an intermolecular thing or something.
Yeah,
I got it right. Just want to make sure that I wasn't just like guessing.
Yeah.
I guess the other one was difference between making esters, Fischer esterification versus ethyl chloride plus alcohol. Is there a difference between the two?
It depends if you want to heat the crap out of something or not. So like Fischer esterification, you need to heat it up real hot with acid. Acid, chloride, and alcohol, you don't need to add any external acid. Heating things in acid is not always a great idea, but because you might have other functional groups that'll start falling off and doing E1s, SN1s, or whatever. Whereas the acyl chloride plus an alcohol, you can have leaving groups elsewhere in the molecule and it doesn't matter. They don't care. Whereas if you heat something in strong acid, you're probably going to start doing SN1s and E1s all over the place.
Yeah.
So it depends on the complexity of your molecule.
Mm-hmm. All right. I think this is the last one. This doesn't make sense.
Right.
I don't know what I was thinking. This question is, I did this one I made these questions yesterday at like 2 in the morning, so I guess I was fine.
So you're asking, is that SN1 or SN2? I think under those conditions, it's secondary. We do not have a strong base present. And secondaries are right on the bench. But what I'm seeing, like heat in there, I'm thinking, okay, mostly SN1 like. And then the major product is going to be the nucleophile coming in opposite the large bulky isopropyl group. If it's SN1, if it's SN2, the product, yeah.
Okay.
Methanol, it's not so much that methanol is too weak as I'm indicating that if this was a primary, it would definitely be SN2, but secondary, it can go both, and methanol is pretty weak, and there's heat added, so I'm making high energy intermediate, so more likely that we're going for SN1E1.
Okay.
So more question. Oh, I guess this one. Okay, this one I had. Like we know how we said we deprotonate this, and we form the ring.
Yeah.
Is there at any point in time where this is too sterically hindered where we can never actually close the ring?
No, not for ring formations. Okay, a tertiary is not too hindered, but if you had a tertiary surrounded by tertiaries, that might be too hindered.
Okay.
I don't know if anyone's ever tried that.
But generally speaking, it usually will fall through with the SN2.
Right, just because it's held together, it can't avoid it. And the 5,6 just it folds properly. It can work. But never intramolecular. But intramolecular, yeah, we can do a ring closing like that.
Okay, I think that's all the questions I had.
Okay, we're gonna skip on to whoever's next in line then. This is fast. Okay, Chloe.
Hi, Dr. Trent, how are you?
Good.
Okay, so my first question is from the carbonyls assignment that you posted, like from the previous assignments, and it's question 1G.
Okay.
I don't know if you want to pull that up on your end.
I'm gonna pull it up on my end.
Okay.
And I will share my screen so that everyone can see what we're talking about.
Okay, sounds good.
Okay, there we go. Question 1G down here. Sodium borohydride, 0 degrees.
Right. Okay, so in your answer key, it says that there's no reaction that would occur. Right. So I was just wondering, like why that would happen. I know in your answer key it says like needs heat, and I also had another question, like if it was instead of the NaBH4, if it was lithium and then
yeah, that's fine. That works fine on an ester. So sodium borohydride selectively reduces carbonyls only, isolated carbonyls, ketones and aldehydes. It can do that at basically anything. It can reduce esters if you heat it. So
I didn't understand that.
My phone agrees with this class. So if you didn't, if you look this up in a lot of textbooks, they'll say, hey, sodium borohydride does not reduce esters. That's a lie, it does. You just need to heat it. But at 0 degrees, it does not reduce esters. Lithium aluminum hydride will reduce esters at 0 degrees. Lithium aluminum hydride will not reduce acids at 0 degrees. You need to heat it a lot to reduce acids, but it can reduce acids. So temperature matters.
Okay, that makes sense. And then just to go along with your point, so H in that case, like the same question, but H, so that would occur and then it would attack the, right, in the ring, right, okay.
It'll attack the ketone, but it wouldn't be able to touch the ester. Yeah.
Okay, that answers those questions. And then from assignment 1, question 9H.
Yeah. Share screen. Go on. Yeah. So this is. So I didn't number them. That was smart. A, B, C, D, E, F, G, H. Okay, this one.
No.
Or you're going the other way. Okay.
No, it's the one above. It's the one above that. Yeah.
Okay, that one. Yeah, I'm sorry, I didn't number them. Yeah. Okay,
so just regarding that one, so in your answer key, I didn't put what you put, like when breaking the double bond and putting it on the oxygen with the H3O. Yeah. So you put the positive charge next to the
oxygen.
O methyl group. Right. Yeah. Why did you put the positive there and not on the carbon above that?
Okay. What can the oxygen group do anything with the positive charge of this carbon?
No, it can't.
Are you sure?
I didn't think so when doing the question.
What is the hybridization of the oxygen?
Sorry, I don't know what you mean.
What is it? Is this oxygen? Is this sp2, sp3?
Oh, sp2.
Right. Why is it sp2?
Just because it has the double bond and then it has the methyl group attached to it, and then it has the 2 lone pairs, or the
So
1
why
lone.
does that make it sp2?
Because it has an extra.
Right, it's sp2.
It has an extra p orbital.
Right. Why does it have an extra p orbital?
I don't know, because it's sp2. I couldn't.
Because it can do resonance with the double bond.
Oh, okay.
Okay, so let's say we do resonance with the double bond. We have a resonance structure. We have a double bond between the oxygen and the carbon here, and a negative charge up on this carbon, and a positive charge on the oxygen.
Okay, that makes sense.
Okay, so if you generate a positive charge here, it can be stabilized by resonance with the oxygen, whereas a positive charge here and a hydrogen here cannot be stabilized by resonance with the oxygen.
Okay, and then regarding the question below it, so that would be the same case with that question. So the positive charge.
Yeah. Well, it can't actually do resonance with the nitrogen.
Right.
So, because the nitrogen has all of its electrons tied up, so the positive charge is going to avoid this spot like the plague because the nitrogen is already positively charged.
Okay, that makes sense. Okay, thank you.
Again, you have to think about what this means. It means N plus double bond oxygen, and there's no way to get that N away from being N plus. It is N plus or N2 plus. And so it cannot do any resonance into there. It's going to never want to have a positive charge next to it. Yeah.
And when doing a question like this on the exam, would you like us to draw out the resonance structures to explain this?
Like the
full
question say, show the mechanism, predict the product of the following reaction. So you'd have to show the mechanism. And so it'll probably be a good idea to justify why your mechanism is going that way. If I just said predict the product, you do not need to draw anything except the product. But if I say predict the product and the question's worth 3 marks, if you just draw the product and you're wrong, you get 0. If you draw your mechanism and your mechanism kind of goes right, kind of go wrong, you get part marks.
Okay, just when you did your answer key, you did draw out the resonance structure, so I was wondering if we would have to do that for.
You don't have to. I did to explain why.
Okay, that is good. Okay, thank you. That's all my questions that I have.
Okay. Aryan.
Hello, sir. Good morning. Right, let me just share my screen really quickly. Okay, can you see my screen?
Yeah.
All right, so I guess for this question, I was wondering why it wouldn't be 2/4 because from my notes, it said the group would like go onto the carbon that's like makes the most stable connection in like acidic conditions, but this this O methyl group, like that would be the least hindered carbon, no? Wouldn't the
sorry, what was the answer to this question? The answer was C.
Yeah, the answer is C, which is 4, but I put B, which is 2, because under basic conditions.
Sorry, just give me a second.
Oh yeah, sorry.
Because I think the question's wrong. Selected answer B, correct answer is C. That's 4. MCBA. Yeah, the answer key's wrong. I'm changing the answer key right now.
Okay, cool.
It's a typo in that, so I'm going in and doing. What question was this? Question 1?
This is question 1 for me, yes.
Okay, yeah, I am updating that right now.
I guess while you're on my assignment, my question 9 was the same as the one Megan brought up earlier, and I think you said the answer key was wrong for this.
It's been regraded.
Oh, okay. For everyone, okay, cool.
Yeah, I changed the answer and it automatically regrades it.
Okay.
Miracle of science. Okay, so this was. Can you just scroll back up to your question there? I just want to, yeah, because obviously I just ported the wrong answer. Edit. Okay, so I'm just doing one last check to make sure I didn't just typo myself.
Yep.
Yeah, we definitely need attack under basic conditions. The answer is B.
Awesome. All right. Do you want me to stay on this for a little longer, or should I go to my next question?
You're good. You're good.
Okay. This was a question from my midterm, I guess. So essentially, my answer and the answer key's answer like matched up exactly the same, except the oxygen I have circled here. I wrote its hybridization could be sp, while the answer key says sp2. I just felt like, yeah.
It can't be sp2. Okay, so we'll talk about, or it can't be sp.
Right.
So if you're sp, what is the geometry between the two sigma bonds?
It's going to be linear.
Right. Okay. So the angle is 180 degrees.
Right. Yeah.
You can't make a 6-membered ring with a linear atom in it.
Okay.
Try as hard as you can. Like, I understand why you wrote SP, because you're like, hey, I can go double bonds both ways. Like, you can, there's a resonant, I can draw on paper resonance structure where it has two double bonds, and it's gonna be, but it'll be 2+, which would be a little weird, but whatever, shit's weird, it's fine. But the real problem is it can never access that geometry.
Okay. Okay.
So it can never be SP, even though it can go both, it can go left and right with the double bonds. It can't do them at the same time because it can't be SP. It has to be SP2.
Okay, yeah, that makes sense. Okay, so when we're talking about rings, like, because I just remember for the resonance structures, like previous, like whenever I do them, like even if it's like super unstable, if it's possible, I account for it. But,
Yeah,
like, for
but
this, it's just not
I would
possible.
say the double positive would be beyond the pale.
Gotcha.
So I would expect, even if that was linear, that would be SP2, because it's just, it would have to be 2+ to have that. And it's just like, and it's neutral now, and so it's just not going to do that. And there's no other positive charges. Like, if there was like lots of positive charges on a molecule, I'd go, okay, maybe an argument for this could be 2+ to help stabilize that in one resonance structure. But the whole thing's neutral. You're never going to generate 2 charges on something if the molecule as a whole is neutral.
Yep. Okay, yeah, that makes sense. I guess for this question, yeah, essentially, well, maybe I should do it side by side, actually. Okay, so essentially, my answer key goes on a different page, but that page is, it was just the Newman structure, and the Newman structure matched up.
If you did talk about the A values for this one, I'll accept that, because didn't we change the answer on this one? Yeah, I basically, if there's a good explanation with the A values, I have accepted your answer. So what did you get on it?
Let me check really quickly. I'm pretty sure I lost a mark on this.
Doesn't matter. Send it to me.
Okay.
Great correction.
Okay, sounds good. Yeah, that's
as long as you drew the structures correctly. I didn't check that too carefully.
Yeah.
Boom, boom, boom. That looks good. Yeah, no problem. Yeah, you should get full marks.
So I think, like, this is just for future situations. So it would be better to look at the A value compared to the.
Yeah, you're right. Your A value is a better value.
Okay.
This
cool.
was just a poorly worded question.
All right. Yeah. So that's basically all my questions. Thanks for the help.
Okay, Jeanette.
Hi. Can you see my screen?
Yeah.
Okay. So I'll try to be really fast about this. So this question, I was debating between E2 and SN2, and I was just wondering why it's SN2 and not E2.
Primary leaving group, very small nucleophile.
Okay. So is this not strong base? Like I read.
Strong base, but it's also a strong nucleophile.
So does that like predominate?
It's case by, so no, it's not true. Almost all strong nucleophiles are strong bases. And almost all strong bases, the atom itself that is involved in making it a base is a strong nucleophile. Now, the rest of it might make it too bulky. So then what you have to do is you have to balance bulkiness. So in this case, we take a look at this and go, we're definitely in the E2 SN2 category. We're under basic conditions. Then we take a look at the steric bulk of the nucleophile and go, okay, it's a methoxide, it's small, it's kind of stick-like. I take a look at the electrophile and go, okay, there's no resonance, there's no double bond present, so there's nothing favoring conjugation energy from E2. My leaving group is primary, so it's very accessible. So I have a small nucleophile, I have a very accessible leaving group. I'm perfectly set up for an SN2.
Okay. Then, so this question, we were just talking about it. So I thought that it would be both. These are my like mechanisms. I don't know if I'm just thinking about this wrong.
So under acid, you're right. Under base, you're wrong. because base attacks the more accessible proton or more accessible carbon. So under acid, we have this argument about this charge thing. It's like the bromonium, where the bigger positive charge is and all that. And that's why you attack the one you did on the bottom. But at the top, the three-membered ring is not inherently charged with the epoxide. So your base is looking around and going, what's the most accessible place to attack? Oh, it's the secondary carbon, not the tertiary.
Okay.
So it attacks the secondary carbon.
Okay, and then just a quick like general question. I emailed you with a regrade request for the midterm, and I haven't seen a mark change yet, but it was a question that we like talked about in office hours last time, and you said like
I just might not have gone to it in the last.
Okay.
I just haven't done the regrades the last week or so.
And then for questions that
You'll get an email from me saying it's been corrected. You'll see.
Oh.
There'll be an email chain. Yeah.
Okay, thank you. For questions that are like, is this diastereomer an enantiomer meso compound, that kind of thing? I seem to have like trouble with them. Like it's been an ongoing thing, so I'm trying to correct it before the exam. And like the like I don't know if it's just like seeing the like rotations is a problem. So is like doing RNS like the best way to go? Would you recommend?
If you have trouble with the rotations, then yes.
Like I thought I didn't have trouble with it, but I don't know. I like keep getting those questions wrong on assignments. So I was just wondering if like RNS would be the way to go.
Then maybe RNS is the way for you to go. Yeah.
Okay. And then for SciComm, if I have a YouTube video, can I just like my assignment be a Word document with the link to my YouTube
absolutely.
video? Okay, and that's all my questions.
And any references that you feel are necessary if your YouTube video is kind of abstract or something.
Okay.
So some people write a little paragraph with a reference or two, like just or whatever relevant references. Like it doesn't need to be long or anything. Your assignment's YouTube, but if you're feeling that it could be misinterpreted, then it can be useful to write a very short piece.
Okay, that's all.
Okay, Madeline Garlati, because we got two Madelines with the hands up.
Hi, can you hear me?
Yeah.
Okay, so I just have a few questions about the assignment as well. I don't know if you already went over them. For question 3 with the...
You'll have to share your screen.
Oh, sorry.
Because everyone's question 3 is going to be different.
Okay.
Randomized.
Let me see. Okay, can you see?
Yeah.
Okay, so I was just confused why this would be E2 because like I thought that
yeah, we did go over this one. So I think it wasn't covered. I didn't cover it in my lectures live that I've done this year, but the posted ones, I've talked about tertiary amines being strong bases. So it's not quite like they are even though it's a neutral molecule, you're under basic conditions, and so you are favoring eliminations. They're also really, really, yeah.
Okay. And also for this question, I thought, yeah, I got confused because I thought it would follow the Zaitsev rule, right?
So it should, but what is another condition of the Zaitsev rule? For E2 elimination, what do you need to have?
For Zaitsev?
For any E2 elimination, what's required for an E2 elimination?
Like a strong base.
Yep. What else?
The solvent.
Yep, that's fine. What about the nature of the leaving group and the proton and the hydrogen coming off? Do they need a special spatial relationship?
Yes.
Yes, they do.
Okay.
Do you know what the spatial relationship is?
I'm drawing a blank.
They need to be 180 degrees from each other, or anti-periplanar.
Oh, right. Yes. Oh, yeah. Okay.
Can the hydrogen that leads to B be 180 degrees from the chlorine?
No.
No, because it would have to be a trans cyclohexane, like a axial, and if the chlorine is axial, the hydrogen would be equatorial because that carbonyl would be axial. You cannot get that hydrogen that leads to the Zaitsev product to be anti-periplanar to the chlorine. So it cannot do an E2 elimination at that site. So although it wants to do the Zaitsev, it can't.
Oh, okay. Okay. Was there any other one? I think that one was, that was the only other one I had a question about. Okay.
I'm going to move on to Christian then.
Thank you.
Yeah, no worries.
Hi, Dr. Trent.
Hey.
I just have a quick SciComm question.
Yeah.
So, if you remember from last week, I mentioned I was thinking of like making it look kind of like a nature documentary.
Yeah.
So I did that, but in the process, I kind of just ripped clips off YouTube.
Yeah.
And I just totally stole them. So should I like reference these YouTube videos I got the clips from? Okay.
Absolutely. So in a document, so if you're making a YouTube video, because what sounds like what you did is you ripped off the video and then you provided new audio, right?
Yeah, multiple videos. Like I kind of chopped them together.
It's creative. You're kind of remixing. I've got no issue with that, but I think in your Word document you should sort of say, hey, these are the original videos that I use the video from. If it's up on YouTube, and it's not like if it's not somebody who's illegally posting material that is copyrighted by other people, then it's under a fair use license. And I think what you'd be doing, even if it was copyrighted material, it shouldn't be up on YouTube, but your use of it would be fair use because you're doing new creative material. So you just need to cite where you got it from. Yeah, and just use that in the accompanying Word document that is your submission.
Yeah, makes sense. I have one quick question from your practice assignment for carbonyls.
Yeah.
I'm going to send a little picture in the chat.
Okay.
So you have this little arrow that flips around the double bond.
Sorry, I'm looking for one you put. Did you put in chat a lot earlier or?
Oh no,
there
it's
it is.
probably
Okay,
still
there it is. Yeah. Yeah. So what I'm doing there is I'm saving. I'm a lazy fuck. That's what that comes down to. So what I should draw is the double bond going up onto the oxygen, drawing intermediate, where we have the nitrogen, the chlorine, the oxygen, and the other carbon all attached to that carbon. So the carbon's attached to 4 different atoms.
Okay, yeah.
And then the oxygen, the negative charge on the oxygen comes back down, reforms the double bond, kicks out the chlorine.
Okay, that makes sense.
So what I'm doing there is I'm kind of telescoping 2 steps into one. And you should probably draw out the intermediate. It's just I'm really used to drawing it this way, and I probably shouldn't have my answer.
Okay.
Yeah.
That's all I had. Thank you.
Okay. Cool. Madeline Rempel.
I posted my questions in the chat.
Okay, Madeline, take a look. There we go. So on a scrap piece of paper, draw the curved arrow mechanism for the following reaction. Once you determine the major product, draw the space below. Remember. So this is looking for acetal formation. So if anyone wants to follow along, you can find Madeline's first question in the chat. And so what you're...
First, use your fingerprints to unlock the device.
I really fucking hate that. I don't know how to turn it off. You protonate, so I know it's listening to me all the time. You protonate the ketone. And then the alcohol attacks that carbon to make a hemiacetal. So you make sort of 2 bonds to the carbonyl carbon from the oxygen that's currently attached to it as a carbonyl and the new oxygen that's an alcohol. When you do that, you're going to rotate it into a ring, and that's going to change. Those are both down wedges right now, and they're not going to stay that way because of the way you're going to have to rotate bonds. So one's going to stay a down wedge, one's going to become an up wedge. And I think that's where people are getting this question wrong when they're putting it in.
Okay, thank you.
And the second question, I think that should be an SN2 in my mind. So I think it should be inversion of configuration of the carbon with the chlorine that's currently up being replaced by a methoxy group that's into the plane. That's my guess. If this is in an elimination chapter, though, this is actually very similar to my Zaitsev question in that the methyl group below is in the antiperiplanar position to the chloride, so you can't eliminate along there. You'd have to eliminate to make the less substitute double bond, like the less favorable one, because the more favorable one's not possible to form.
Okay, thank you.
And then you emailed some questions as well?
Last week, I think.
Oh, okay. That is fair.
You don't have to go through them. You have other people, and I can probably get them, but it's okay.
Okay, well, you know what? How will you go through them? And then if you can't, I'm holding office hours on Friday. You have #1 priority if you show up. You just basically bump everybody.
Okay, thank you.
Okay. And then Alyssa.
I think someone was before me.
No one's got their hand up.
Okay.
Down the hands. Jeanette and Christian still have their hands up, but we've already talked to them. I think they just haven't dropped their hands.
Okay. I just, based on what Dea said on one of his questions, I was confused because he said that the KMNO4 reagent would produce ketones and not like OH.
So he had a special condition where he was heating it with base. So I talked about that in the, I think I have an example on one of my assignments, and I also talked about that in the recorded lectures. So KMNO4 with base cold just generates COH. KMNO4 with base hot keeps reacting because it's hot and it just kind of destroys everything in sight. And it does a mechanism that's actually kind of akin to the ozonolysis. And it breaks open the carbon-carbon bond that was a double bond and generates two carbonyls.
So you'd say that they would probably like yield the same product?
The
ozonolysis and
yes, and hot KMNO4 with sodium hydroxide. Yes, they do.
I don't remember seeing that on the assignment. Do you remember which one it was on?
Let me go check. I think it might. Dea might have gotten that from one of my lecture notes.
Yeah, I don't think it's on the assignment.
It might not be. Let me just check to find out that one. Yeah, I don't tend to focus so much on that for this one. I think I always just state it's cold. Like I have a question. Assignment 2H definitely says KMNO4 but cold. Right. Just gonna check assignment 1A. Nope. Assignment 1. Yeah, I don't think I've assigned a question like that, so you're not gonna get that mechanism. But
okay. And then
it is a thing.
Okay, got it. Yeah, I just don't remember. I can't remember seeing that in the.
Yeah, no, I don't think I've done it. So you're not responsible for it.
Okay. And then I just want to clarify something that Melissa said. I just didn't even think of this until now, but the Newman projections with double bonds. So I remember seeing something in the textbook questions, something about like it was actually a Newman, like a chair like drawn with a double bond. So if we are asked to draw like the product of a mechanism and it has a double bond, would we include that double bond just normally, just like you just put a second line on the chair?
Yeah. Technically, if you have a double bond in a 6-membered ring, it cannot adopt a chair. It adopts a twist boat conformation. We haven't talked about twist boats. There's enough going on. Let's not. So yes.
Okay, so yes. Should we like kind of like, I don't know. I don't know if there's any practice on that, and I'm worried about that.
I won't ask you to draw a Newman projection with a double bond in a chair.
Okay.
Normally, I'm interested in Newman projections as the starting material because that helps explain how you get the double bond. But Newman projection of the product is less interesting.
Okay. And I had just another question. So when you're going from starting material to product, like if it's an endothermic reaction, then don't you have like your
your product is less stable than your starting material. So if you asked to draw the Newman projection, we would draw the starting material, not the product.
I'll be clear what I'm asking you to draw the Newman projection of.
Okay. Okay.
I'll always be very clear what I'm asking you to draw the Newman projection of. Yes. Okay.
And then I just want to double check. So when you open up an epoxide under acidic conditions, you like if there's like a methyl group or whatever, and if it's less accessible, you would attack the like most hindered spot, and then if it's basic, you'd attack the most accessible spot.
Let me rephrase your first part. So basic, most accessible, absolutely. If it's under acid, you attack the most stable carbocation. You attack the site of the greatest positive charge.
Okay, got it.
And it happens that is the tertiary site, which is the most hindered. But it's not because it's the most hindered, it's because it's the site of the greatest positive charge.
Okay, got it. All right, that's all my questions. Thanks so much.
Okay. Hi again, Megan.
Hi, I had a question for our the carbonyl assignment.
Yeah.
It was question 3F.
3F. Just need to minimize everything. I'm just going to call it up and share my screen. Okay, 3. This is not the carbonyl assignment. This is the carbonyl assignment. 3F. Okay?
Yeah, just looking at the answer key, I was wondering why at step 3 you didn't just deprotonate the alcohol.
Oh, you want the answer key. Okay, well, let's see if this... Shit, where did I put the answer key? Because of course I don't have the answer key sitting in my folder. Can you share your screen if you have it open? If you don't, I can pull it up.
I don't think I have it open.
Okay, give me a second here. I'm just going to pull it up under here.
Practice assignments, more problems.
There we go. Thank you. Thank you. I was looking at it. I have no idea what I'm looking at. There's way too many resources. I add more resources every year, and I keep thinking, hey, this year I'm going to provide enough tools that everyone's going to do really well. And then it doesn't work that way. Okay, 3F. So.
Yeah, like at the third step.
This step here?
Yeah.
Why didn't I do what? Sorry?
Like, why didn't you just take off the hydrogen and then stop there?
Oh, okay. Because I'm in, that's a really good question. It's because if I was in water, absolutely. Right? Absolutely, completely. But I'm in methanol. And so at this point, there's nothing stopping this from continuing. And methanol can now just replace the water. Why is that favorable? Because I'm sitting in methanol. So I've replaced a water with a methanol. And that's a good trade when my solvent is methanol. If I now put this into water, if I took this out and I stuck into water under the same conditions, I would go back to stopping here with the, just taking off the hydrogen, having the alcohol or the OH. But it's because I am in methanol that the methanol is going to drive out all the water.
Okay. All right, that makes sense. Thank you.
Yeah. Okay. I think I'm only 20 minutes late for my next thing, which is fine. They can freaking wait. This is important. Thanks, everybody. I will chat with you on Friday if anyone shows up, and last class tomorrow.